Welcome to the second day of the SE webinar on SEAM CO₂. After this short introduction, we'll hear from Mike Failer about geophysical acquisition and response. Then I'll cover information about using the models and data in various different ways. Nick Reese will talk about subsurface monitoring using backscatter. And then Mike Branson will talk to us about using the CO₂ dataset to drive innovation in efficient monitoring solutions. Then we'll have an open Q&A session.
This morning I'm going to talk to you about the geophysical acquisition on the SEAM CO₂ project, geophysical models. I'll talk about both the acquisition and some of the processing that we have had done on the data that we acquired. This is an outline of the topics we will cover, not in any particular order, but included we'll talk about the models, we'll talk about the active seismic processing or acquisitions and some of the processing done on it, on the data, on 4 models: the contained pilot model, the leaky pilot model, the contained pilot model with near surface heterogeneity, and the marine gas depleted reservoir model. Included in that, I'll talk about the microseismic events that we simulated on the leaky pilot model that were done so we could understand something about the microseismic response of the models. This is a vertical cross-section through the injectors of the pilot model, showing various features within the model. For example, there's a sealed fault on the west side. There's a fault on the east side that allows fluid to migrate horizontally through it. And in some scenarios, in what we call the leaky case, fluid can also migrate along the fault into shallower reservoirs. The main reservoir is located at a depth of about 2 kilometers. It's about 400 meters thick. There's a cap rock shown here in red. I should say that the base model is the porosity. So the cap rock is shown in red. Above the cap rock is a mid-level reservoir. It's about 100 meters thick, which is where fluid flows when it migrates up through the fault or through failure in the cap rock on the west side. It also fluid can also migrate up in the fluid migration scenarios into a shallow reservoir at about 500 meters deep. I'll run you through the geophysical properties of the various baseline models. I'm going to show you a series of slides that are all basically identical scales, both in properties and in physical dimensions, just so we can compare the models. This is the baseline model. This is before anything has happened in the pilot model. It's a land model. I think Stephanie described this yesterday. This is the model after 30 years of injection. Again, Roman yesterday talked about how the injection was modeled and the output of that. This shows the 2 injection wells. Again, there's a well to the west of the western fault, and there's a well to the east of the eastern fault. You can see the P-wave reduction in the region where fluid has been injected. This is 30 years after the start of injection. Again, you can see similar things in the density and a little bit in the S-wave velocity, and you can see some variation in the Q properties as well as a result of the injection. In the model with fluid migration up the eastern fault, we call that simply the leaky model. The fluid migrates up the fault, and this is the main reservoir here. And you can see then it goes into the reservoir at mid-depth at 9 years. And I'll show you an example at 30 years. But it just migrates up into this mid-level reservoir. It also starts migrating through the cap rock on the western side, through failure in the cap rock, up into this mid-level reservoir as well. At 30 years, the fluid migrates all the way up to this shallow reservoir along the fault, and you can start to see some velocity reduction here due to both the presence of the gas as well as increased pore pressure. in this region. The pore pressure reduction extends quite a ways away from the fault going to the east. On the western side, the fluid only goes up into this mid-level reservoir. I'll now describe some of the acquisitions that we've done on this pilot model, and I'll describe some of the data, the acquisition geometry, some of the data, and a little bit about the imaging that was done. So there are several acquisitions that were done. They're listed here. The ones in red are data that were imaged, and I'll show some of the images from those. So we did a full 3D seismic acquisition on the baseline model and 2 of the monitor models at 30 years. That's the contained model and the leaky model at 30 years. We did 2D seismic, and by 2D seismic I mean it's 3D simulations with shots and receivers located along lines. The migrations I'll show are 2D. We did those on the baseline, the same 2 monitor models that we did at 30 years, but also a monitor model at 9 years in the leaky model case. We also did VSP, which I'll talk about. VSP was collected in 3 wells, the baseline in 3 monitors. We collected data that can be used to calculate downhole and surface DAS response by taking spatial gradients of velocity traces. And those are collected again every time, basically on all these models. And we simulated microseismic events on the leaky models. This shows the 3D surface seismic geometry on the pilot models. The green model, the green box, well, the background is V sand, which gives you an idea of where the reservoir is. And this is an integrated V sand, so it shows roughly the spatial extent of the reservoir in the horizontal direction. The white wells are the injection wells. The black triangle is a monitor well that we use for VSP, and the yellow dots are gathers that we're showing over here on the right side. The red dots are surface shots that we collected. Shot spacing was 150 meters in the east-west direction and 300 meters north-south. On the right side, I'm showing gathers on the baseline model and on the leaky model at 30 years, and you can see the difference. You can see new events here in the data collected on the leaky model that are due to the presence of the CO2 within the reservoir. This shows where traces were collected. Again, we collected traces over the entire model on a 50 meter by 50 meter grid. We also collected data in all 3 well bores, which are sort of a pseudo 3D or pseudo VSP acquisition, except that it's fairly low frequency. It's 40 hertz maximum frequency, but they were collected at 50 meters spacing and depth, ranging in depths from 0 to 3,000 meters. And at each location, we recorded 3 component velocity response. This shows the sources that we used. The left 2 show the source used in the surface seismic simulations. The top trace is the time history, and the bottom is the spectrum. It's a linear plot of spectrum going from 0 hertz out to 70 hertz, and you can see that this is roughly flat between about 10 and 35 to 40 hertz, and you can see it's a symmetric pulse in the time domain. For the VSP simulations that I'll describe, and for the microseismic simulations that I'll describe, we used a higher frequency source. Again, this one is flat roughly between about 15 hertz and 80 to 90 hertz. So again, it's got the same properties as it's a Clowder pulse, and the only difference between this one and this one is basically the higher frequency content. This is the image we obtained from migrating the surface seismic data. Again, the data were collected with an absorbing upper surface. The migration was done in 3D with no pre-processing of the data. Using the absorbing upper surface sort of eliminated the need for some of the pre-processing. The imaging was always done with the baseline velocity model. So even though the velocity structure has changed, for these simulations, we decided to use the baseline velocity model. So you see the sag in the lower reflectors for below the main reservoir, or actually reflectors off the lower part of the reservoir. There's a sag due to the fact that we used an incorrect velocity model. We also collected some what we call 2D surface seismic and VSP data on this model. And by 2D surface seismic, we mean that they were actually 3D simulations where we just had sources and receivers located along lines. And there were 4 lines, so we made sure we got at least a walk-away line for each well. We recorded these simulations were actually shot twice. One is using the same surface seismic source that we used in the 3D acquisition, and once we call it a VSP acquisition, but we also collected data on the surface, and the only difference is we used a higher frequency source. So here is the comparison of the 2 simulations, the 2D surface seismic simulation and the VSP simulations, identical source locations. Receiver spacing, we used a higher, smaller receiver spacing at the surface for the VSP simulations with higher frequencies. The borehole receiver spacing went to 2.5 meters from 5 meters. And you see the source was different. The VSP simulations we did with a free upper surface, and the source changed from an explosive source for the surface simulations to a vertically directed source, and the trace length is different. And this shows images obtained from the 3D data on the right side. This is the 3D migration calculated using the 3D data. This is the 2D migration calculated using, again, it's 3D simulated data, but only collected along the east-west line going through the receivers. So these are both along the same line. So you can see the difference in the image quality we get when we do a full 3D image and when we do it just image using the data along a line in 2D and using 2D migration. I want to talk a little bit about the microseismic simulation. The first thing we did when we started defining this was we described all the things we thought we wanted to do with these data. And I won't go through all these in detail, but there are things like testing location methods, testing moment tensor inversion methodologies, looking at magnitude estimation, collecting data for network design, and so forth. So there are a whole bunch of things we want to do, collect data that we could evaluate methodologies for processing data to determine information about what's going on in the subsurface. Because of that, we decided to collect two different kinds of events. The first set of events that I'm showing here, this is an east-west cross-section through the model. So depth goes from 0 to 4,000 meters. And east-west, you can see it's a one-to-one cross-section. You can see the events here are defined to fall roughly near the faults. And this is where the geomechanical model said that the events should occur. But in this case, these events, at each point, we calculated 6 simulations, one for each of the components of the moment tensor. And this was so we could be agnostic about what the moment tensor is to be and allow the user to specify whatever moment tensor they want by summing the results from the 6 simulations. So those simulations are available. Again, we calculated things on the 3 different models: the baseline, the leaky model at 9 years, and the leaky model at 30 years. Some of the events were actually simulated at the same location in all 3 models, so we could look at the differences in the waveforms with different structures, and I'll show something about that in a minute. So we used these three velocity models, some events simulated on all three models, some events simulated on only one model. Then we also calculated a larger set of events with fixed moment tensors. And these show, again, the models calculated on the three different models color-coded by which model we used. In this case, the moment tensors were specified roughly to be consistent with slip along the faults that the events are near. We added some noise to the moment tensors so that they wouldn't all be identical moment tensors. So there's some fluctuation in the moment tensor, just to make it a slightly more interesting data set. Just to emphasize that one of the things that's important to SEAM, has historically been important to SEAM, is validating the simulations that we get to make sure we get the right thing. And one of the things that I spent a lot of time on was to make sure that AGT, who did the simulations, and me were in agreement about how to define the coordinates for a moment tensor. But we did that by simulating an event in a homogeneous medium, where we could calculate what the P-wave rate. This is the P-wave amplitude and polarity measured at near the surface for this simulated event at depth, calculated using formula from Aki and Richards, calculated using a reflectivity code, and calculated by AGT. And just to try to show that you see the characteristics of the simulations are all the same. The Aki and Richards is a little different than the other two, and I think that's mainly because of my color code I used for scaling these. But this gave me, convinced me that we could see polarity reversals from positive to negative in these. We could see a nodal plane running through here where the amplitude is 0. And this was consistent between AGT and our reflectivity calculation that convinced us that we were transferring information from us to AGT in a manner that was consistent, so that the events they calculated were in agreement with the events that we wanted. This shows the S-wave radiation. I'm not showing polarity, I'm just showing the amplitude. And again, I'm showing the result from Aki and Richards. I'm showing the result from reflectivity that I calculated, and I'm showing the result that AGT gave us. So it shows a pretty good consistency between our result, or the expected result, and what AGT did for us. Now I'm going to show you waveforms for an event that is located beneath the reservoir and recorded at seismometers located near the surface in three different models, so we can see how the waveforms evolve over time as the presence of gas changes during the injection time. So the event is located along this eastern fault below the reservoir. This is showing a velocity reduction in the main reservoir. This is showing the velocity reduction in the mid-reservoir because fluid is leaked up into that reservoir along this fault. And then also there's a velocity reduction in the shallow reservoir at about 500 meters depth. There's also a fairly strong pressure signature within this part of the reservoir as fluid gets injected, as gas gets injected into this. I should say that this is the velocity model at 30 years in the leaking model. I'm going to show you waveforms calculated in the baseline model and in 9 years after injection and after 30 years of injection. These are S-wave waveforms recorded at near-surface receivers, and I've aligned the S-waves on roughly manually picked arrival times of the S-waves, just so I can show more of the S-wave structure even as the offset increases. So these are calculated in the baseline model. Again, the event is at the start location. This is the baseline velocity model before there's any fluid injection. Now I've overlain in red the waveforms calculated in the model 9 years after 9 years of injection. The blue background are the baseline waveforms. The red are those calculated in the 9-year model. The background is the 9-year model, so you can see in red, roughly in the velocity model, where the fluid has gotten after 9 years. It's gotten into this middle reservoir, but it hasn't yet reached this upper reservoir. You can see some delay in the S-wave arrival times, particularly for the waves that have propagated directly through the reservoir. There's some delay in the S-wave arrival times. I think there's a little bit of delay over here as well, and I don't really know the rate paths, but I suspect they may have gone partially through this western reservoir, but I'm not quite sure. There is a little bit of delay, which could be due to propagating through this, or perhaps there's some slight velocity reduction in this region due to pressure increase. And now these are the waveforms calculated in the after 30 years of injection in green, overlaid on the baseline waveforms shown in blue. Here you can clearly see delays in the S-wave arrivals due to propagation through the reservoir. The reservoir is fairly well evolved by 30 years, and they've also propagated through this shallow reservoir. They've propagated through this perturbed shallow reservoir. So the S-waves are significantly delayed here. I should say that I've shown the waveforms I'm showing are about 1.5 seconds of data. You can also see some changes in the coda of these due to some changes in scattering as well as Q changes, attenuation changes in the model. So the coda is not only delayed, but it's perturbed due to scattering changes. Again, the background is the velocity model after 30 years of injection. Now I'm going to talk a little bit about adding near-surface heterogeneity. You saw when we did the simulation and imaging on the baseline model, the images were pretty good, and there was a sense that those were unrealistically good, and we wanted to see if we could add some noise to the model to make the images look a little more realistic. And we did this, and I think Joe described this yesterday, by adding near-surface high velocity, and I think Joe described the geological context of that, and I think Bill will describe that in the subsequent talk. But we added some near-surface high-velocity heterogeneity. Again, this is the original model. This is the near-surface heterogeneity. Joe and I experimented with probably 20 different models to try to find a model of heterogeneity that gave us images that we thought were realistically noisy. So this is the model we ended up with. And one thing about this model is that the heterogeneity is increasing from west to east across the model. So the worst part of the image resulting from the near-surface heterogeneity is going to be on the east side of the model. Again, just to show you the properties, this is the noisy baseline model. Now the noise was added in the same manner to both the baseline and the monitor model. So we only calculated traces of waveforms on the baseline model and on the contained model at 30 years. So again, this shows the velocity model with the after 30 years of injection with the reservoir, the wells penetrating the reservoirs and showing where the velocity changes occur as a resulting of CO2 injection. The acquisition on this, we decided to focus our acquisition over the main part of the reservoir. Again, this is the gas saturation that I've showed previously. The blue shows the region where shots were placed on this spacing. The green shows the region that we targeted for imaging, and the yellow shows the simulation region. We wanted to make sure the simulation region was bigger than the imaging region, so we could catch any out-of-plane reflectivity coming back into the data. These are waveforms calculated in both the original baseline model and the noisy model. They're 2D elastic simulations that I did, but just to show the effects of the absorbing forces versus the free surface and the noisy model versus the non-noisy model. So the upper left-hand gather is an east-west shot gather, again for the source at about 6 kilometers, the middle of the model. Calculated on the original baseline model using an absorbing upper surface. If we add a free surface instead of an absorbing upper surface to the original baseline model, we see the gather on upper right, where now you see there's a significant amount of noise, in this, particularly in the center of the gather due to the slowly propagating surface waves, but it also tends to contaminate the later arrivals that would be useful for imaging. The lower left-hand gather shows the 2D simulation on the noisy model with an absorbing upper surface. And compared to the upper gather calculated on the original model, you can see the gather is more noisy, particularly in the center part of the gather, in the near source part of the gather, but also just the reflection, the image, the quality of the reflections is degraded. The right-hand lower gather is calculated on the noisy model with a free surface. Again, 2D simulation, elastic. This is with a free surface and the noisy model. Now you see, again, significant degradation, particularly compared to the one in the upper left-hand corner, where the reflection events are really degraded. They're not clear in a lot of the parts of the data, and there's a lot of noise here due to surface waves and surface wave scattering. These are 2D migration images calculated from 2D simulations on both the noisy model and the original model, calculated with an absorbing surface and a free upper surface. And again, I've used a series of shots calculated across the model for the imaging. So the upper left-hand image is the one, again, that I calculated using 2D simulation and 2D Kirchhoff migration, just to show you what the best case of what the image would look like. If we add a free surface instead of an absorbing upper surface to the original model with no added near surface noise, the image quality degrades quite a bit just due to the influence of the free surface. And we saw that in the previous slide where the shot gathered data looked significantly more noisy, particularly at near offset. The lower left gather is the one calculated using an absorbing upper surface on the noisy model. So the simulations were done with an absorbing upper surface on the noisy model. Again, 2D Kirchhoff migration. You can see the images actually degraded from the one calculated in the original model with an absorbing upper surface. Again, the noise has degraded the imaging. On the right lower image is the 2D migration Kirchhoff migrated image calculated using data simulated with a free surface on the noisy model, and you can see the image is pretty bad. So we're going to show the simulations that we had AGT do for us were in 3D with the free upper surface. The image in 3D actually will be quite a bit better, and that's due to differing effects. You get more noise in the 3D data due to out-of-plane scattering, but you also get reduced noise in the image due to the benefit you gain by increased stacking. And here's the proof of that. The left side is the original model simulated with an absorbing upper surface and imaged in 3D. And this is the noisy model, again simulated with a free upper surface and imaged in 3D. You can see that both images are pretty good. This image is degraded, particularly on the east side, where the heterogeneity has been increased more than it has on the west side. The west side looks pretty good, but the image is definitely degraded here. And I think Bill will talk about that in the next talk as well. One thing we did during this acquisition was there was interest in what happens if the receivers are not actually placed at the correct location. So we called this dithering, and what we did is these are subsets of the receiver array, and this is the southern part of the network where the receiver dithering was small. So you see that the original and the dithered receiver arrays were both shown in blue, red and blue, are pretty much in the same location. But as we went to the further edge of the acquisition region, the dithering was increased, and you can now see that the dithered receivers are located quite a bit different than the original receivers. we did restrict the maximum receiver shift to be less than the receiver spacing on the regular grid. If you look at the gathers, you can see the difference between these two if you actually overlay them. The difference is fairly subtle. Unfortunately, we did not try to image with the dithered data to explore what the impact of the receiver dithering was on the image quality. On the noisy model, I've basically concentrated on the shots that were placed in this blue box and the receivers that were in the green box and the imaging that was done. I'm sorry, the receivers were within the yellow box and the imaging was in the green box. What I hadn't told you was that we also acquired a high density line of receivers going across the model, as well as borehole data, pseudo VSP data, and here are the parameters of those acquisitions. What I've described to you so far is what we called part 2 of that acquisition. Part 1 was test simulations. Part 2 was the acquisition for imaging. And part 3 was a set of simulations that we did to get long offset data. And in this case, we put shots outside of the region where we had previously put shots. In other words, they're outside this region encompassed by the blue box. So all the blue dots are shots outside that region. And we put receivers then in a way that we could collect long offset data that could be used for FWI or other kinds of processing. And here's where the receivers were. So the receivers covered the entire model, so you could get long offset data that's as long as the model would allow. The final model I want to talk about is the marine gas depletion model. This shows the geophysical properties prior to production for the model. Again, I think Joe and Roman discussed this model yesterday, but this is the model that was built for prior to production. Roman described the reservoir evolution of this model. It was first produced. There was methane in this part of the reservoir at the anticline, and there was a production well put there, and it was produced. We decided to make the post-production model the baseline model for the CO2 injection study. And this shows the geophysical model after the CO2 injection into the lower unit. The injection was down dip from the main reservoir, and it was in actually a lower reservoir that was isolated from the upper reservoir by a shale stringer. So the injection well is shown here, and this is the velocity reduction associated with the injection into the lower unit. And this shows the geophysical properties after the injection, 25 years of injection into the upper reservoir. Again, the injection was in this region, so there's some additional velocity perturbation in here after the production of methane due now to the injection of CO2. I should say that you can't really see it in this here, but the lower part of the reservoir, I'm showing it over here in the density model, the lower part of the reservoir continues to evolve as the gas moves within that reservoir during the time that CO2 is being injected into the upper reservoir. So the acquisitions we did on that, again, this is a marine model, so the acquisition was designed to be a little bit different, but we did do an acquisition that centered on the main part of the model, again, where the CO2 is in the region shown by green. The region we wanted to image is shown in this box with green. We put a series of shots within this blue box that would be used for the imaging, and we collected two sets of receivers for this. One was a push-pull type streamer set that might move with the shot location. So it's a high density, it's 12.5 by 12.5 meter grid of receivers going from edge to edge of the simulation grid, and it's centered on the shot, and it extends north and south of the shot. And as the shot moves, the north-south extent of that receiver array moves. So in those we collected both pressure and VZ near the surface. We also collected OBNs on a 50 meter by 25 meter grid shown here in red. With the OBNs, we collected 3-component velocity 1 meter below the seafloor, and we collected pressure 1 meter above the seafloor at all these positions. We also collected, as I'll show you in the next slide, more information, high-density seafloor receiver lines, sub-seafloor receiver lines along 2 orthogonal cables. The east-west had actually 5 cables parallel that I'll show you to allow people to calculate the strain rate tensor within the region of the cables, so that unconventional DAS acquisition geometries could be mimicked if desired. And the north-south was just a single buried receiver array collecting 3-component velocity. As I said, the east-west cable was actually consisted of 5 cables, and this is the sort of a vertical cross-section through the cable geometry. So there was a central cable, and then there were 4 cables centered around it at spacing roughly about 2.5 meters in these direction, where we collected, again, 3-component particle velocity that can be used to calculate DAS strain rate, the full stress strain rate tensor if desired. I should say we also collected borehole data, 3-component receivers every 2.5 meters from the surface to 4,000 meters depth at both the production, the 2 injection well bores, and then at reservoirs located north of those as well. So there's VSP type data. Again, it's 40 hertz maximum frequency, but VSP type data at 6 wells down to 4,000 meters depth. Like we did with the noise model, we wanted to collect some far offset data. There was interest in that. And we did that simulation as a reciprocal C4 node noise model only on the baseline model. And the idea was to collect data that could be used for FWI type processing and maybe other studies that you people might think about. But we did this, we put up the shots at C4 nodes 1 meter above the surface. They're explosive sources. And then we collected data near the surface, 1-component velocity. We recorded pressure at near the surface at 7.5 meters. So the pressure was collected at the same depth that we did shooting at in the active experiment. So it's a reciprocal geometry again with the shots at near the seafloor and the receivers at the surface. So again, the idea was to give us some long offset data that could be used for things like FWI. And this shows where the receivers were located at the surface. Again, we didn't collect them over the entire model because the data set is quite large. We just collected them basically within the region where we had simulated shots in the acquisition used for imaging. This slide shows a comparison of traces collected at various locations and various properties. In the marine gas depleted model, the upper left-hand panel shows the Z component of velocity collected at 20 meters depth for a shot near the surface near the center of the model. It's an east-west shot gather. The lower panel shows the pressure data collected at the same set of receivers at 20 meters depth for the same shot. The middle 2 panels show the data near the seafloor. The upper panel shows the Z component of velocity collected a meter below the seafloor for the same shot, same east-west gather, but just data collected a meter below the seafloor. The lower panel in the middle shows the pressure data collected 1 meter above the seafloor for that shot. The upper right-hand panel shows the data collected on the cable that was buried a few meters below the seafloor with sources at 2 meters below the surface. 2.5 meter source spacing. Again, it's Z component of particle velocity. And the lower panel shows Z component of particle velocity collected as a function of depth within one of the boreholes. And this shows the images that we got Again, this is the post-depletion image. So you can see again the top of the reservoir is imaged pretty well. That's what this is the reservoir or the well that was used for production. And now this is after the injection into the lower unit. You can see that this lower unit, there's a reflector off the top of it and some structure within that reservoir. Again, the migrations were done with the baseline velocity model, so you can see some pull down in the reflectors here below the reservoir or in the lower part of the reservoir. And then after the injection, the upper unit, and this is the wellbore that was used for injection, and you can see some difference between these images, indicating where the CO2 is gone during the injection into that part of the reservoir. That concludes my talk. Thank you for your attention.
Yeah, thanks, Mike. I guess we have a couple of minutes if people have questions. The Q&A box is there for you to type questions in. And I don't think that we have many questions yet for Mike, but we'll wait for a few seconds if anybody has something urgent that they'd like to ask. And then, oh, I see. There is a question in here. Mike, can you see this all right?
Yes.
Good.
I've got to read it here. To get this synthetic seismograph in your simulation model. Bill, that may be one. I'm not sure if he's asking about getting SEAM data or how they should simulate their own data, but not enough info about the geology.
Okay.
I'm not quite sure I understand the question.
Well, let's do this, Mike. Let's see if we can't get you to help out Ibrahim with an opportunity to answer that either by in person or by email. Does Ibrahim have your email address, Mike?
Not sure. I can try to figure out how to add it.
Well, I don't think that he'll be able to see it, but you could possibly tell him.
Oh, okay. Okay, my email address is my name, Michael.Fehler, F-E-H-L-E-R, @gmail.com.
Okay. Great. So, Ibrahim, feel free. Go ahead and email Mike, and you guys can set up a conversation about your question. And we have Ibrahim's email also, Mike, in the Q&A box, okay?
Okay, I'll try to grab that. I'm not all that familiar with this application, so I took a screen grab, so I've got it.
Great. All right. Well, thank you very much, Mike.
Thank you.
That was a great presentation. And so, Robin, I think we're ready to move on to the next video. Hi, I'm Bill Abriel with the Society of Exploration Geophysicists, the SEG Advanced Modeling Corporation, and today I'd like to speak to you about SEAM's CO2 sequestration simulation project, how to use those models and data for benchmarking and for experimentation. SEAM is an industry cooperative for large-scale numerical benchmarks. We bring together organizations like those you see listed below for collectively designing and implementing simulations on difficult problems. So there's no complications here from operator liability for live field data. And we're doing things that are a lot cheaper than field experiments. The subsurface geology is exactly known. And we can handle all geophysical data types at any sampling. SEAM was established in 2004. Our first project was subsalt modeling, which was crucial for benchmarking subsalt imaging. The second was unconventionals, and trying to appreciate what geophysics can and cannot do in determining the fracture and the sweet spots for unconventional projects. Then a foothills model, and the foothills was a very difficult overthrust regime with a jungle-like environment and topography. Then an arid model. The arid model is karsted topography that generates a great deal of coherent noise. Then we did integrated work in pore pressure and also 4D field work, life of field. Then an artificial intelligence project. And currently we're finishing up the SEAM CO₂ sequestration project. In the SEAM CO₂ project, we've been working with 8 different participants, and each of those participants that you can see their logos here are Chevron, ConocoPhillips, Shell, Oxy, Total Energies, Saudi Aramco, SLB, and Woodside, who have been contributing direction and resources and intellectual property for us to be able to design great challenges. So we have worked on 4 different scenarios, the first being a land project scenario that you can see up here in the upper left. And in that scenario, what you can see is injection of CO₂ in turbidite sequence. The next project that we worked on was similar, but what we did was to add coherent noise from the near surface, which creates a great challenge for data processing and interpretation. The third is an injected CO₂ but not contained, and so the fault that runs through here is going to have CO₂ not contained and injected then into aquifers above the reservoir unintentionally. And the final project is CO₂ injected in a marine case in a lower reservoir down here, followed by injection in this, which is a gas-depleted reservoir. So we're going to be talking about these 4 different projects. So why generate benchmarks, and how do we use those? Well, primarily because we know the right answer. These are challenges for accuracy of seismic interpretation so that the presence and saturation of CO₂, when we say we can see this and do it accurately with seismic data, we know that we're correct. Secondly, it helps illustrate what the reservoir dynamics are and what the value of information is for monitoring. It's a nice illustration, shows the sensitivities, and it's really good for teaching and training. The third element of using benchmarks would be that if you can piece together all of the things that go into building a perfect digital twin, then you've got everything you need to improve that workflow, and you can do experimentation and vary parameters. So what exactly are the goals of using benchmark information for measuring, monitoring, and verification of CO₂ saturation and pressure? One thing is to measure what are the realistic resolution and detection limits of the geophysical tools as we practice them in the field. The other is to identify specifically what the relative value is of each of the techniques that we use, 3D monitoring, VSP, 2D gravity, and how they relate to each other. So let's look at model 1, where we've got a combination of 2 injections of CO₂. Here's the reservoir simulation, the CO₂ saturations after 30 years. And what you see is that you've got injection in multiple zones in the turbidite here and also here. When you take a look at the geophysical parameters, you can see the reservoir here is low velocity, but you can also see now this high resolution infusion of CO₂ and injection in these 4 different fairly large lobes. The 3D baseline information of seismic data, you can sort of see the reservoirs, but it's only when you get the 3D monitor after 30 years you get to see the lower resolution but quite clear information from the seismic data of where the CO₂ probably is. You can see 2 things. First of all, you can see a combination of the amplitude information increasing, and secondly, you can see down here there's a time shift and a time sag. So the idea now is to take this data, which has got amplitude and time information, and invert our way back here to CO2 saturation. Now let's take a look at this experiment. This is a turbidite sequence, and you can see it comes from here, and the V sand is thick over here. There is an injector here in white, another injector over here in white, and an observation well in black. So the question is, how do we get the geophysical information that represents a good experiment for this? First of all, we've got 3D seismic data time-lapse, which is nodal, high density of your shot in every receiver. Secondly, these lines here are 2D seismic high-resolution lines. And there's also VSP in all three wells. It's high resolution, and gravity data, both downhole and surface, and DAS information, both downhole and surface. The concept is to take a look at each of those geophysical techniques and ask the question, what are the limits? If you used only VSP, what would you get? If you used only 2D seismic, and how often do you have to shoot 3D seismic data to make it worthwhile? Okay, now let's take a look at some other experiments that we can use this data for. First of all, these data are suitable for benchmark processing experiments because we have the known and exact answer. And one point of that would be position repeatability. If it turns out that your geophones are in a slightly different location, how sensitive is that? Secondly, seismic sampling tests, e.g. Compressive sensing. That's an experiment that you can run with this data to find out what your limits are. And then thirdly, seismic noise elimination, and we're going to talk about that in just a second. So let's take a look at this first model, which is a land-based model, and ask the question, how about repeatability? We did, in fact, acquire, again, a second time, a 3D seismic survey in 4D where we moved the receivers to a different location than the exact centers in blue. So that sets us up for a really nice experiment in data processing to see how sensitive that really is. So let's take a look at another noise challenge. In this model 1, which is land-based, the near surface was noise-free. Here it's an absorbing upper surface, but we were able to do two things to that, one of which is to turn on the near surface noise generators, and secondly, also to introduce noise generators from the perspective of small scatterers in the surface, and this seriously degrades the data, as you can see from the stack. And let's talk about what it looks like in the shot gathers. Okay, here are the shot gathers, and over on the left-hand side, you can see what a shot gather looks like with an absorbing upper surface. Here's 3 seconds of data. And you can see quite clearly here what it looks like when you get a reflection from the reservoir. Over here, we've got a shot gather with that free upper surface, and so therefore we're generating a great deal of coherent noise. In addition to that, we've got the near surface scatterers. So this is quite a challenge. We need to be able to find this signal in this data. Okay, that was model 2. So let's move on to model 3, where we're not going to contain the CO2, but in fact, here's the reservoir simulator that shows that when you allow the CO2 to open up through a fault, we're going to see it come up into this aquifer just above and all the way up to the surface up here. This one, there is in fact also leakage in that fault, and so you get to see the CO2 come here. What we're going to do is we're going to be able to get seismic simulations of this event, and we're going to see exactly what it is that seismic data can do to recognize the early breakthrough. Okay, so here's model 1 where we contain CO2, and you can see the turbidite and the CO2 saturation from the reservoir simulation. Here, what we've done is allowed for the seal and the caprock to break, and it turns out it's slow leakage along pipes that come up into this aquifer above this. And in this case over here, what we have is we have a fault that you couldn't detect seismically with zero throw. But it turns out that it does in fact leak, and it leaks into this upper section and all the way up here into the upper zone as well. And here's a three-dimensional view of that. And here is the P wave velocity of that uncontained CO2. What you see here is the velocity anomaly associated with the CO2 as it comes and pokes its way through the capillary seal. And over here you can see where the CO2 has come up into an upper aquifer along an unresolved fault. And as it continues up that fault, we want to see this with the VSP and the 2D seismic data and the gravity data as it comes up and works its way to this very shallow zone up here. And this is what the seismic expression looks like. We've got high amplitude information at a low resolution over here for the escape of non-containment of CO2 into that aquifer, another one over in this aquifer, and it makes its way up the fault here to the shallow aquifer. This is going to be a really excellent challenge for full waveform inversion. That velocity challenge is going to be able to get back to that high resolution velocity we saw just a few minutes ago. Now, the geomechanical portion of the simulation allows us the opportunity to see where mechanical failure is going to trigger seismic events. And in this upper section here, we've got an event that occurs here, and we've got a receiver up here. And now at 0 years, you can see what this reflectivity looks like over here in the blue trace. 9 years later, it's a little bit different. 30 years later, somewhat different because we've got CO2 here and we're acquiring data through that zone. The other location that we've got is somewhat different. This is another location down here, event number 2. And if we look at receiver number 1, number 2, then we can see that we're going through a combination not just of the CO2 that's injected, but also the 2 zones, one here and one here, that are much thicker with respect to CO2 saturation. And we can see that each one of these is going to have a change in the coda and a change in time. So there are lots of these events, and we've got receivers everywhere, and it sets up a really, really nice tomography problem. We're going to move on to Model 4, which is now going to be marine, similar stratigraphy, and what we've got is a depletion of gas in the upper zone here with well number 1. Well number 2 is going to inject CO2 in the lower reservoir, and then well number 3 is going to inject CO2 in the gas depleted reservoir. So here's the timeline. Gas depletion happens for about 40 years, and then you get CO2 injection in this lower zone over here for about 30 years, and then injection in the upper zone. This is the reservoir simulation gas saturation for the end result after having depleted the gas reservoir here. Then we've got injection in the lower section with well number 2 and CO2, and then injection here in the upper zone. And this is the gas density at the end of gas production and the 2 phases of CO2 injection. Number 4 is a shallow water marine setting with pressure phones on the ocean floor and velocity phones also on the ocean floor. What we get then is we get reverberations from the hydrophones and a different set from the geophones, and they're complementary when pulled together. You get an excellent combined high-resolution data set. So this becomes an excellent data set for testing, combining pressure and velocity recordings. This is Model 4, and this is the seismic data collected at the end of the gas depletion. The reservoir is here, and you can see this really nice bright spot, and also the gas-water contact right here. Then the 3D seismic data after another 30 years of injection of CO2 generates a strong amplitude response here in the lower reservoir where it's injected, and also if you look carefully you'd find the time sag associated with that. And then after 30 years of injecting in the depleted gas reservoir here, we've got the final seismic representation of the reservoir management. As a benchmark, we're trying to use this seismic data to reverse the process and make our best estimate of where the gas saturation is for CO2. One of the elements of this, of course, is we've got amplitude variation with angle, and you can see the angle stacks here from 0 to 16 in the first section, 14 to 31 in the section that's the mids and the fars, and you can see in the fars offsets we've got a really excellent representation of the gas in the upper zone that's residual, the gas water contact, and the lower CO2. Let's look again at the reservoir simulation of the depleted reservoir here. This is gas density and the injection of CO2 in the lower zone. Then this is the gas density of the injection in that upper zone of the depleted gas reservoir. This is the pressure content, and you can see that the pressure is decreased significantly in the upper zone, but then increased again when we injected CO2 in that zone. We're going to take a look at some of the substantial differences in data over time for the reservoir in this complex management. This is the impedance difference after gas depletion, which is only in the upper reservoir. You can see that you've got a fairly substantial impedance change. That impedance change is like 0.1 relative to water-filled reservoir, and that impedance change is due to a decrease in pressure because we've bled off the gas, but not all of it. Decrease in pore volume because with less pressure we've got squeezing the volume of the pores down, and an increase in the water saturation because the gas is less. So therefore we've got this overall hardening. In addition to that, you can see in the center of this diagram a red line across there, and that's because the water level in the gas water contact has risen, and that the water has then invaded the gas zone and changed the reflectivity. So fairly complicated response. Now the impedance in the lower section after 25 years of CO2 injection in that lower reservoir shows a very significant change in reservoir softening, and the reservoir softening is because we're putting a gas, CO2 in this case, into an aquifer, and that being the case here where you can see the two injections in the upper and the lower zone is increasing the pressure. That happens over the entire reservoir, an increase in pore volume also, and a decrease in the water saturation. Decrease in the water saturation means that we're softening up the reservoir in these dark blue zones. And here's where it gets really interesting, because now we're injecting CO2 in that upper gas depleted reservoir, and what we have is CO2 replacing methane, and so therefore what you have is a hardening. You have CO2 replacing water down here, so it's a softening. And over time, we've had a movement of the CO2 up dip, so we're softening with CO2 replacing water here, and then migrating water replacing CO2 up here. Pretty complicated. Thus finally, by the time we're finished with the management of the reservoir, we've depleted the gas in the upper reservoir. We've injected CO2 in the lower reservoir, and then we've injected CO2 in the gas-depleted reservoir. And we have both a hardening and a softening of the reservoir, as you can see in red and blue. Red being the hardening, and blue being the softening of the reservoir. And when translated to the simulation of what we've got for reservoir parameters at a 5-meter scale, you can see a combination both of increase and decrease, blue and red, at very high resolution, because that's the resolution we carry the reservoir at in our simulation at 5 meters, and that has got a very complicated set of changes in reflectivity. The question is, what happens if you actually shoot seismic data and you've got a wavelet to worry about and resolution. So when we convolve a wavelet with that high density reflectivity, we've got a very complicated set of reflectors. And the trick then, of course, is to take this information, which is going to be 4D related, and this is the theoretical 4D, and try to work our way back to the gas saturation and presence that we know we have on the basis of designing the benchmark. So let's talk about using the data. We have got simulations now for time steps, and let's talk about how to get the differential for something, in this particular case, the lower injection of CO2 in that lower reservoir from T90 to T45. Here is the seismic difference in the injection in that lower reservoir between those two time steps. And you do, in fact, see a very strong CO2 saturation signature here. You also see the pressure increase here in the reservoir in 4D, and very, very faintly, you can see some differences up in here. Those are actually pressure increases from the geomechanics. The question is, my gosh, what is going on here with all of this information, which we know is not reservoir related? Where did that all come from? And this is a combination of this multiples and mode conversions in the data that you can now see are very significant if you're doing 4D work. Let's look at those angle gathers, and I think that what you can see is that at the reservoir level, we've got some really nice, strong, consistent flat reflectors, and that's fine. That's exactly what we're looking for. But it turns out that in addition to that, you can see these curved ones here, and those are a combination of multiples and mode conversions in the data in a noise-free case where we don't have any information from the top. There's no multiples, there's no shear waves. This is just simply the internal reflectivity system. So the complication is that trying to get perfect 4D data is going to be a lot more work than just subtracting two data sets. Well, that's a nice way of taking a look at the challenge of trying to get seismic data and resolution and handled correctly with benchmark information for saturation, pressures, and location. Let's talk about one other thing that this is all intended to do, which is to be able to enable us to build digital twins faster. What does that mean? What that means is that if we're going to use geology and flow dynamics and geomechanics and derived earth properties from seismic data to actually build digital twins that match what we're doing, we need some examples where we know the right answer and we also have all the parts in place. This is a set of data sets where everything is available, and so in order to build and effectively run a digital twin process, we should be able to streamline this workflow much more quickly as long as we know where all the parts are and how they fit together. This data set allows us to do that. The other thing that this particular type of data can be used for is not just benchmarking, but also, as we pointed out, workflow efficiency. And also, we have the opportunity to change parameters and find out through good benchmarking information what the sensitivity is for things that we don't easily handle in our work in reservoir management. So here are some examples of reservoir simulation challenges that can be investigated by using these data. CO2 absorption, dissolution of CO2 in the brine, the fingering of CO2 and sinking over time, fluid mixes and phase changes. We don't know what the effect is going to be overall. We've got some good ideas, but this is a data set that we can go back and recycle and actually find out what our thoughts are. Also, building on this models, one of the things that we can do is we can actually do better simulation practices in terms of multiple effects in geomechanics. We should be able to link the geomechanical practices to the reservoir simulation practices such that we can actually trigger those seismic events at the same time that they're occurring. We can also take a look at stress-induced anisotropy from those velocity changes. The effects may not be big, but they could be important to us in the long run. And these are data sets where we can accept those challenges and make those measurements. So in conclusion, SEAM has generated 4 scenarios of reservoir simulation from a geology viewpoint, flow, geomechanics, and geophysics to help us to appreciate how benchmarks can be used to challenge the accuracy of our seismic interpretations, what tools are going to be best for us, how we can design MMV practices. In addition to that, we have got some excellent illustrations of the impact of CO2 monitoring in gas depletion on land and in also in the marine case. And we also have providing a complete data package for improving the workflow and also for experimentation. I think that these are good data sets for benchmarking and are really going to help the industry. So that's the end of that particular presentation. And if anybody has questions that they'd like to ask and want to put in the Q&A box, we'll spend a minute here and see what we can answer. So Felix asks, there is mention of digital twins. In my understanding, digital twins involve decision-making and optimization under uncertainty. What are your thoughts to include this in the future? I think that's a really good question. I'm not real sure I know how to go about doing that, Felix. I would love to have a conversation with you about that, though. And it's easy for you to find me. I'm online, Bill Abriel at yahoo.com. I'd like to get your thoughts as well. But I do think that you'll be able to see a little bit more information about that if you stick around for Mike Branston's talk, because I think he's starting to address that using this data. Well, if we don't have any further questions at this time, Robin, I think that we're ready to move on to Nick Reese's video.
Good morning. Thank you for allowing me to share some of my research. My name is Nicholas Rees. I'm a multifaceted geoscientist with upstream exploration production experience, predominantly on the UK continental shelf. I'm currently in my final year of Shell-sponsored research, focused on reducing the costs associated with subsurface storage monitoring. The title of my talk today is Rationalized Subsurface Storage Monitoring Using Backscatter, under the supervision of Professor David Waltham and Dr. Chris Willesee. The research comprises of 3 fundamental interdependent components: model, validation, and application. This is where SEAM comes in. In the model component, we identify signals that do not conform to conventional primary reflection trends, or signals that are not derived from horizontal interfaces. We are interested in signals derived from subvertical geometries. We then generate synthetic models to imitate realistic transit paths for these events. Within the validation component, we acquire real data to test the model at a location where the subsurface can be prognosed with a high degree of accuracy. Since the dominant costs associated within monitoring are in the acquisition, a minimalist acquisition configuration is adopted. In the application component, we look to enhance signals through standardized processing techniques and develop bespoke analytical time-based methods to see if we can detect subvertical boundaries using unconventional signals. So, in my title I mentioned backscatter. What is it? Gilmans has suggested that backscatter noise can be defined as two main types: guided waves and side-scattered energy. On the FK spectrum, backscatter appears on the opposite side of the FK plot to primary reflection trends. Now let's delve a bit deeper into the model. There are a number of subdivisions of backscatter from literature. Now I will demonstrate two of the main subtypes of backscatter, one being the reflected refraction and the other being the reflected reflection or the prismatic wave. Here I demonstrate the path of a reflected refraction against a subvertical boundary. The critical incidence angle, or this angle here, is defined by the geophysical properties of the two layers. The energy travels along the boundary of travel at the velocity of the layer below. Within the shot-gathered domain, this appears as coherent linear energy and can be defined by adaptations to the refraction move-out equation by adding 2d minus x, d being the distance to the vertical reflector. The reflected reflection, or prismatic wave, another type of backscatter, has subtle differences. Instead of linear, here move-out has a hyperbolic relationship with time and travels at the velocity of the initial layer. To generate reflected reflections, or prismatic waves, a reflective primary boundary is required, where incidence is near grazing, and consequently the second incidence is closer to normal. Once again, adapting the move-out relationship to include 2d minus x can describe the analytical time relationship for this mode of transit. But what does backscatter look like in reality? Here are three examples. So here we have a marine 2D shot record taken in the North Sea. Here we have a smaller scale onshore survey. And here we have a Kirchhoff migrated North Sea survey adjacent to a diapit. As you can see, these all contain coherent events with an increasing two-way travel time at nearer offsets. Backscatter can also be associated with other geological structures, including steeply declined faults, dikes, and seabed canyon systems. Now I will briefly describe how we validated these travel paths at a reflective subvertical boundary in the near subsurface. So we acquired data at a mineshaft museum in South Wales where underground access is permitted. It was called Big Pit Colliery. Here we employed an end-on acquisition configuration with 24 geophones at 3 meter spacing. The data was pre-processed using standardized techniques to enhance the full wave field. Can I draw your attention to the repetitive negatively dipping signals in green? This is backscatter. But what type? So several techniques were used to attempt to differentiate types of backscatter in the test data. The combination of their results provided the answer. Ray-based amplitude and phase modeling suggested that the amplitudes of reflected reflections or prismatic waves are significantly better preserved than reflected refractions. Bespoke analytical methods, including tau-p cross-correlation, adaptive move-out analysis, and ray tracing, all support reflected reflections as the main method of backscatter in the test data. Now we have determined that reflected reflections can be a prominent feature where you have subvertical geometry. How applicable is this to a subsurface storage facility? Does the edge of the plume itself permit reflected reflections to occur? So unlike a mine shaft, which is highly reflective with a reflection coefficient of near 1, the reservoir brine CO₂ boundary is much more complex. The reflection coefficient of CO₂, using normal incidence approximations, is projected to be around 0.066 and have a boundary that is likely to be gradational rather than sharp. To add further complexity, the anisotropic reservoir properties within a heterogeneous reservoir is likely to create an irregular boundary, as seen in Sleipner. Interestingly, hydrogen boundaries exhibit much greater reflectivity than CO₂. Can we find the boundary in a CCS dataset like SEAM? Using the SEAM data, there are 3 necessary workflows. The conventional mapping approach, here used to define the plume extent and the associated boundaries at a carbon capture and storage site on the SEAM data, and benchmark the 2 other workflows. This is deemed as a conventional approach as it employs fully processed and migrated seismic volumes. Number 2, the rationalized reverse time migration approach. Here we explore how modern methods handle small realistic input data sets. This method is adapted to include PRIS-RTM wavefield separation techniques for isolating backscatter to reduce migration noise as a part of the imaging conditions. The third and final approach is backscatter move-out correction. It is a bespoke method using analytical time travel relationships described within the model sections of this presentation, and was established using the test data to place the mine shaft correctly. In the conventional mapping approach, we must define subvertical boundaries within the data to serve as a benchmark for comparison against RTM and BCM methods. 3 main subvertical reflective boundaries can be identified: reservoir boundary, pressure front, and CO₂ boundary. What do normal incidence approximations tell us about its reflectivity at each of these boundaries? Now, the pressure front boundary is challenging to place. However, average values of CO₂ are 0.07 for the western and 0.09 for the eastern plumes, coherent with the values from literature described earlier. In the RTM method, we isolate 2 shots, A and B, that situate here on the velocity model, and here they are, along 2D lines, and configure them to an end-on receiver array, with the far offset terminating before the start of the western CO₂ boundary. We input the velocity model to varying levels of detail to generate the forward model, replicating realistic input data. For the backward model, after resampling to match migration time steps, we input the elastic shots A and B for the adjoined wave equation. 2 methods of cross-correlation are trialed: standard cross-correlation and wavefield separation. This was the PRIS-RTM technique I described earlier. We separate the wave fields into up, down, left and right components in both forward and backward models, and only cross-correlate the components that relate to backscatter. Post-processing is applied, which includes a dip filter and a Laplacian filter, plus lateral gain correction. So here I demonstrate the RTM results. They're not finalized, but demonstrate the challenges associated with small input data sets. PRIS-RTM approaches that incorporate wave field stripping seem to reduce noise and determine the extent of both eastern and western plume boundaries, where the velocity input data is at full resolution. Standard RTM approaches are noisy, but do show some promise. Other considerations to improve these results may include the input data. Input data is vertical P component. Maybe horizontal P component data may produce better results. Another thing to think about is the elastic versus acoustic modeling. The input data is modeled elastically, however, the wave equations in DeVito are modeled acoustically. Recreating the input data using acoustic wave equations may be more suitable. And then pre-processing the input data may produce better results. Overall, there's much more work to do here. The backscatter move-out correction methodology employs adapted move-out equations, as we described earlier in the model section, to provide a solution for estimating the distance from source to subvertical reflector with depth. There are two parts to backscatter move-out correction. Velocity analysis is standardized and uses normal move-out equations to estimate RMS velocities across the time sample range. Velocity values are then selected and assigned to each of the sample rows for distance analysis. In distance analysis, we provide a range of distances to trial using those velocities. Samples are indexed and placed on zero offset rows against distance to enable depth conversion through Dix inversion. Upon the results to follow, we will overlay the plume boundary defined in conventional mapping to benchmark the results for both for the western and eastern boundaries. So this is the results of backscatter move-out correction for detecting the western plume boundary. Like RTM, we minimalize the input data to an end-on configuration and applied minimal pre-processing. This is one shot gather. A clear velocity trend is identified, selected, and interpolated across to assign each sample an individual velocity value. A range of distances is trialed with those velocities and placed against zero offset against the trialed range of distances. After applying depth conversion and smoothing, we can overlay the boundary defined using the conventional approach. Here we see constructive stacking at the tips of CO₂ boundary extents, a very desirable result. So the same methodology is applied to the eastern plume boundary, but with much poorer results. This is probably because of the residual ground roll and pressure front that we observed in the conventional mapping, or the gradational boundary. But here we can see, again, we have some constructive stacking at the tips of the pressure front. So, learning from SEAM data. The conventional mapping approach managed to identify three main subvertical boundaries effectively. We have the CO₂ boundary, the pressure front, and the reservoir. The subsequent rationalized approaches, including reverse time migration method, integrated prismatic RTM wave field separation, did image subvertical structures using backscatter. Wave field separation reduces migration noise considerably compared to standard cross-correlation methods. The preliminary results suggest that velocity model input data requires significant detail to monitor effectively. Ongoing work may provide better results. Backscatter move-out correction developed at the mine shaft provided promising initial results on synthetic data where CO₂ boundaries are known. What we found was shorter transition zones or better reservoir qualities enhances results using this technique. The western side snaps much better at the tips of the CO2 compared to the eastern side. There may be room for improvement in optimizing a pre-processing sequence prior to backscatter move-out correction. Improved results might come from a hydrogen model or even repetitively stacked shots at the same locations. So where could this fit into a monitoring program? A monitoring program is one that is project specific and uses a catalogue of monitoring methods. Regulatory framework is not yet available to design monitoring programs in most cases. Here demonstrates several identified methods that could be broadly subdivided into surface and reservoir monitoring techniques. Using backscatter may be appropriate in certain situations, particularly in situations with small transition zones. Merits of the technique include a rationalized data set that will significantly reduce the cost of monitoring, but also reduce the time taken to cease injection, for example, should the plume be encroaching a licensed boundary. The aim here is not to replace conventional techniques, but to place an operator in a more informed position to justify the requirement of expensive 4D monitoring workflows. Additional work following this should be test the backscatter move-out correction on real data with varying reservoir qualities, optimize RTM workflows with rationalized data sets and realistic detail of input velocity models. But also ask the question, is there a case for hydrogen storage which offers a more reflective boundary that this might be more suitable? Thank you all for listening, and thank you to my sponsors, Royal Holloway, University of London and Shell. I welcome any questions.
Thank you, Nick. Yeah, we have time for questions. If anybody would like to put a question in the question and answer box, we'll pause for just a second to see if there's something to appear there. So it doesn't look like anything's come forward too quickly. If there are questions, though, just remember you can always type them in the Q&A box at any time. Meanwhile, Robin, I think we might be ready to go on to our final presentation. Mike Branson's got a really nice set of information about how to use the model for business practices.
I'm Mike Branston, and I'm the Geophysical Advisor within SLB, and I've been working in new energy applications for the last 5 years. Prior to that, I worked in solution design and modelling, during which I used the previous SEAM models to help develop innovative seismic acquisition solutions. I've been working with Bill and the SEAM team for the last 3 years, and I'm very happy to share with you some of the ways in which SLB have used the SEAM CO₂ data and review the new technology that it has enabled us to develop. We all know that in the context of CCS monitoring, we are challenged to be more cost efficient. But in this context, what does it mean? Simply be cheaper is not enough. Clearly, we want lower data acquisition costs. We'd also like to have greater insight at a lower cost so that we can proactively avoid negative outcomes. This is very important within CCS as we are essentially operating in a downstream environment. Our work sits downstream from significant amounts of CapEx and investment. Given our monitoring cycles are over many decades and the monitoring objectives evolves as the subsurface risk evolves, we need to look at the balance of OpEx and CapEx over the project. Ultimately, we want to arrive at the right decision quicker while spending less on the journey. Keep this in mind as we walk through the remaining slides. So the topics I will cover today include seismic imaging, 4D gravity feasibility, and then I'll move on to look at some of the new work that includes zonal conformation with waveform coloring, spatial conformance with adaptive sparse 4D FWI, and then we'll discuss how these new techniques can be delivered effectively using digital integration and the utilization of surface DAS, or as we abbreviate it to SDAS. I want to start with a project that was done by Ragda, one of our geophysicists in Cairo, as part of her fixed step training within SLB. The question was, what geometry can we acquire and still produce reliable 4D interpretation products? The project goal was to use the simulated data and the original geometry, decimate it systematically, and then review the 4D metrics to help inform on how we can reduce the cost of future monitoring surveys. The deliverables from Ragda's project included an understanding of the best and most effective acquisition parameters, the optimum imaging technology for future CCS monitoring projects, as well as establishing a library of workflows for future CCS processing projects. So, can we save in acquisition costs? Ragda was able to demonstrate that you could decimate the monitor survey by 24 times and still be able to accurately interpret the 4D signal. She developed a processing workflow using SLB's proprietary noise reduction methods and migrated the data with an RTM migration. I'm not showing the full analysis for you here as we don't have time to explain it in detail, but you can see from the 3D images that the 4D signal is still detectable and the 4D metrics support this. I hope Ragda will be presenting her work to the industry in full in the very near future. Now, moving on, we often ask ourselves, is a route to cost efficiency to move away from seismic toward multiphysics techniques? In this case, can we use 4D microgravity to track the plume migration? This is work that was completed by Yakov and Luciana, who both work within our Milan team. They've presented related work on the Southern North Sea analog model and will be presenting results of the SEAM depleted field model shortly. Here I'm going to show you the outcome from the SEAM aquifer model. Now, in this context, we know that 4D microgravity is a good tool for subsurface monitoring and has been applied to reservoir monitoring in the past, particularly in Norway. What we want to do is to demonstrate how to quantify the application of this technology for CCS monitoring. So the feasibility looks at the applicability by addressing detection, evolution over time, and sensitivity and variations in the injection strategy. The final goal is obviously to support the development of a robust monitoring strategy for future CCS projects. So this is the output from the SEAM aquifer model. We're showing maps of the gravity anomaly, which is the colors, overlaid on the density change, which are shown by the contours, relative to the three cases. So the white arrows indicate where the density change is particularly impacted by the CO2 migrating through the fault. The pink dashed line is the -3 microgal threshold for CO2 and plume detectability, and panels on the right show the cross sections of the corresponding reservoir models with CO2 plume extent 100 years after the start of injection. The well trajectories are displayed in blue and green, and the faults and main horizons in black in those panels. Now, in all cases, a negative anomaly is more pronounced in the vicinity of the eastern well. In case 1, to the conformance case, the negative anomaly in the eastern well progressively decreases over time. This reduction results from the combined effect of injection shutdown and the superimposed contribution of increased density within the pressure envelope around the propagating plume. As a consequence, the gravity signal does not clearly delineate the CO2 plume location within the overpressured aquifer, but more on this shortly. In case 2 and case 3, we can see the eastern anomaly increase in intensity over time due to the upward migration of the CO2 in the open fault on the eastern side. This effect is more pronounced in case 2 since the fault extends into the shallow aquifer. As a side note, the correspondence between gravity anomalies and plume evolution or fault-related fluid migration must be evaluated in light of the gravimeter spacing and placement. And I would direct you to Yakov and Luciana's previous work for more insight on this. But can we do more with the gravity data? Application of edge enhancement techniques to gravity data, such as first vertical derivatives or FVDs, offer further insight. For example, for case 1, where the gravity signal does not clearly delineate the CO2 plume location, the FVD improves the delineation of the CO2 plume location around both the eastern and western injectors. So to conclude on the gravity modeling, the technique is effective at mapping the evolution of the plume within the aquifer model. Look out for the upcoming results for the depleted model. The integrated workflow used is transferable and can be used to assess the effectiveness at tracking conformance as well as detecting non-containment. First vertical derivatives and other techniques enhance detectability of the plume features. And sensitivity analysis and survey design, not shown today, helps us understand the impact of operational and reservoir parameters and should be used in the planning of MMV solutions. That is, what does uncertainty in the reservoir model or changes in the injection strategy mean for detectability and applicability of the gravity technique? I now want to move on to talk about some of the new techniques that we have developed and published over the last couple of years, where we've used SEAM CO₂ data to help validate and verify the model. The first is waveform coloring. This was developed to answer the question, can we locate the plume and detect when it is out of conformance with minimal seismic effort, i.e. a very limited or a handful of shots? So waveform coloring is a method to connect zones in the model domain to regions in the data domain. Effectively, two wave fields are simulated. One represents the full wave field and the other represents the wave field that has interacted with the zone of interest. For CCS, we use the MMV plan, the risk analysis, to define the key zones. So if we look at the schematic at the bottom, we start with the MMV plan and the subsurface model. We then split the model up into zones. We acquire a set of sparse or individual shots, and then we use 4D metrics to interpret and locate the CO2. Now let's transpose that onto the SEAM aquifer model. So we split the subsurface into zones of risk, i.e. zone 1 is the conformance case, zone 2 is the containment case, and zone 3 is the non-containment case. Remember, we are simulating two wave fields, and we are combining them to generate a mask that isolates given areas in the subsurface. We can then use this to track changes in those zones. On the left, you are seeing the zones in the model, and on the right, we are showing the waveform coloring masks for each of these zones. So green is zone 1, blue is zone 2, and red is zone 3. Now the mask indicates where data should change in response to a change in the corresponding subsurface zone. We can therefore use 4D metrics to detect these changes. In this case, we're using the aquifer case 1, the conformance model, and we see in the 4D metric that the change is isolated to the storage zone, so all is well. We can then blind test this with case 2, the non-conformance case, and we see in the 4D metrics on the right that we're now beginning to pick up changes in zone 2 and zone 3, in addition to the changes in the zone 1. This tells us that CO2 is migrated into the secondary storage unit and indeed up into the overburden, i.e. zone 1. Our injection project in real life would now move into corrective measures, and we need to quantify the extent of the out of zone migration. More on that shortly. But first, to conclude on waveform coloring. It is a detection technique that uses limited shots. It delivers lateral and vertical context, specifically whether CO2 remains below a key interface or within a given zone identified and defined by the project risk analysis. It enables multidimensional assessment of plume behavior rather than a binary yes or no indicator. So it can be used to validate conformance and provide an early indicator of non-conformance, all from a very limited number of active seismic shots. The next question we asked ourselves is, can we quantify the spatial extent of the plume without imaging? And the answer is yes. And we developed an adaptive design workflow that enables quantification of the plume extent using sparse 4D FWI. The workflow is as follows. We have a dense baseline that allows us to create a baseline velocity model. We then use the MMV plan to identify zones of risk within the subsurface that we want to monitor. We feed this into the adaptive survey design engine, and the output is a sparse survey that is designed for 3D model updates. We might use this workflow at a given monitor milestone or after we've detected a non-conformance event. For example, if a project has been moved into corrective measures, this workflow allows us to perform 3D localization with FWI, which can then link back to the pre-project risks. Mapping this onto the SEAM aquifer model, we take the output of the quantitative risk analysis. This is a workflow that was derived using the SEAM data as well, but which I don't have time to present here. I strongly recommend you look into Claudia's work on this topic. We take a baseline velocity model, so not the true model, not the model that we use for the simulation, but a model derived from the synthetics using 3D FWI. We then use an automated design process that allows us to identify and select sparse geometries based on their ability to monitor the areas of risk, i.e. the metrics include illumination of a given area, mismatch, and relative cost. The output in this case is a geometry that used 15% of the original baseline source effort to map and monitor the areas identified as being at risk. I'll now show you the results. So this is the baseline case, i.e. a velocity model built using the SEAM synthetics and a conventional 3D FWI workflow. These depth slices at the bottom correspond to the dotted lines in the depth section on the left, and you can see we are pre-injection. So the depth sections or depth slices are getting deeper as they move left to right. This is the baseline case. And now using data from case 1, the conformance scenario, we can accurately reconstruct the plume extent in 3D using 15% of the source effort. Note the plume extent on the depth section as well as in the depth slices. In particular on the left, the plume has not crossed into this upper zone. There's no indication of the velocity response that is associated with the CO2. Now again, we can use case 2, the non-conformance case, as a blind test. So no additional survey design has been undertaken. We are looking to see if the original design is robust enough to capture unplanned events. It should be, because we use the output from the quantitative risk analysis as our monitoring objective. So now you can see the plume extent is well delineated, and we can see the migration out of the primary storage unit on the depth section, and we can also see the presence of the plume in the shallow depth section, or shallow depth slice on the far left. We can also see on the middle and right depth slices the variation in plume character in the deeper sections. So to conclude on the adaptive sparse 4D FWI design workflow, it enables conformance monitoring with a limited monitor survey. It builds on the zonal conformation workflow to provide spatial quantification of the plume extent away from the well. The design process is robust to detect and quantify non-conformance and non-containment events. And the output can be used to recalibrate the subsurface model, which is important if we have moved into corrective measures. I now want to pull this work together and introduce you to a digitally enabled monitoring solution. Now, it reduces acquisition costs, gives us greater subsurface insight by increasing the frequency of monitored time steps, allows us to proactively manage our subsurface risks, changes the balance of OPEX and CAPEX through the life of the project, and ultimately allows us to arrive at the correct decision while spending less time and money on the journey. So over the last 5 years, we've demonstrated the viability of surface DAS as a seismic sensor. The horizontally deployed fiber optic cable, when combined with digital accessibility, provides flexibility in monitoring objective for the life of the project. An example sketch of an installation is shown on the left. Once in place, we can extract a multitude of answer products from a single system. Now these include pressure envelope development, seismicity detection, passive monitoring of plume evolution at depth using ambient noise, zonal confirmation of containment and early detection of non-containment, quantification of the spatial extent of the plume, for example, if we have a non-conformance event, and ultimately derivation of plume properties for model recalibration if required. Now, these are all real examples that have provided critical information to CCS monitoring away from the well in real or near real time. So to summarize the key answer products, they are enabled by horizontally deployed fiber optic sensors, but can work on conventional systems. There is a change in monitoring concept from full field imaging to scalable and targeted detection schemes. We integrate passive and active source technology, so using ambient noise. Some of the insights are shown here include fluid front monitoring, pressure front monitoring, seismicity detection, and ground motion. And importantly, when combined with SDAS, we can harvest this data as often as we want and digitally integrate it into our MMV operations. On the right, you can see the scalable answer products in the system. Today, I've shown you zonal confirmation and waveform coloring and spatial quantification with adaptive FWI, which were both developed on the SEAM data. If you want to know more about these other solutions and how they fit together into a system enabled by SDAS, I have a reference for you at the end of the presentation. So what the system delivers is a reduction in OPEX cost, improved people efficiency, a reduction in environmental sound exposure and the carbon footprint of the monitoring operations, and we achieve this by moving away from large acquisition crews and utilising existing infrastructure when available. Now, I want to conclude with a few short remarks about the SEAM consortium and collaboration in general. The quote on the left is one we overuse in support of survey design and modelling or forward modelling projects, but I think it is highly relevant. We have seen the impact of the SEAM projects have had over the years on solving key subsurface imaging challenges, and I would argue the challenge the SEAM CO₂ project was set up to address is grander in scale and potentially more important. Its objectives are not just technical, but also critical for the wider implementation of CCS as a whole, i.e. to provide a digital twin that can be used to make monitoring more cost efficient, safer, and better understood by practitioners, regulators, and the public. Now, I'm a big supporter of the value of collective engagement and collaboration at all levels, and personally, I've greatly enjoyed the interaction between the participating companies, and I believe that collectively, we have learned a lot. The image on the bottom left is one of my favorites. Hopefully this work will trigger you and help accelerate the work you are currently conducting. Please connect. Please don't look on from afar like the owl in the top right. So I'll leave you with this reference, which will take you to an in-depth review of the adaptive monitoring system built on the back of SDAS. If you want to learn more, my email is listed. Contact me on LinkedIn or pull me aside at the EAG annual event in Aberdeen this June. And with that, I would like to thank you for your attention.
Thank you so much, Mike. I think that was really well done, and there may be an opportunity to answer a question. We've got a question box here, and I see that Ibrahim Mohammed says, is the SEAM model valid for CCS injection and monitoring to be done without seismic data? I guess you could answer that in part, Mike. What you did was you presented the gravity data, correct? And I don't think that DAS counts as seismic, but maybe it does. There was also another question from Ibrahim. If we only have the experimental data of CO2 injection, can we use the SEAM model to interpret the geochemical issues for the reservoir? And the answer is we haven't gone down that road a lot just yet. But the changes in geochemistry are going to have an impact. And I think those are some of the experiments that we're set up to do. And I say we, the idea is for folks to get access to what we're doing in the SEAM models and do their own experiments. So thanks again, Mike. I appreciate that very much. We are at the end of the video presentations, and there is an opportunity if anybody would like to ask any further questions overall. We have most of the presenters are still online, and we can possibly answer any of the questions that you have. So we'll pause for just a minute and see if anybody has any specific questions for this 2-day presentation.
Bill, there are a couple more questions. One from Felix and one
There
from
are.
Abraham.
Let's see. Let's talk about the first one. Felix said, "Oops, sorry, guys." Felix says, "The elephant in the room is the extreme uncertainty we have to deal with." Agreed. How are you planning to address this in the context of SEAM? Risk mitigation and operation optimization all call for capturing uncertainty in a principled way. One way to do this is to use data assimilation, ML, and control. Any thoughts? I don't know. Have you got any thoughts, Felix? We're open to suggestions. The whole point is that we're trying to go down the road and use everything we can with numerical simulation, where we know the right answer, to be able to set things up so that we don't have to spend our time in the field expensively, where we also don't really know the right answer. So again, I'd be happy to chat with you about that. You have my my email, I hope, and I think it sets up a really good question.
And Bill, Abraham is asking about how to get the data. And I think that's a good one. I'd prefer to defer to you on that because you understand the logistics of data release better than me. Or at least you're in the decision process on that.
Oh yeah, no, thank you very much, Mike. That is true. We currently the way that our project is set up, the folks that are participants have a license for confidentiality for a 2-year period before it's available for public use. And so we've just now been getting some of that information into the participants' hands, right? For instance, the gas depletion model. So it'll be a 2-year period before that information is widely available. But the pilot work that we did some 3 years ago now, that data is just now coming into the public domain. So I think that we're going to see an opportunity for access to that data over the next couple of quarters. And that includes the land data set with 3D data, 2D data, VSP, DAS, you know, the baseline work. Yeah. So stand by. We're not quite ready to be in a position to release that information, but we're preparing to do that. And I see, Felix, you pointed out that please see my digital shadow paper and various SEG abstracts and GJI, right? Thank you.
Bill, it
Well, it
might be
looks
worth
like we're...
because Bill Abraham is
Sorry.
also asking about other data, and Joe did respond by email yesterday about the EM data, and I'll try to summarize. And Bill, you correct me if I get it wrong. We did do some testing of EM response and found that the signal was way too weak for the reservoir at measuring at the surface. We did try using, again, a simulation using boreholes as sources to try to get the signal down into the reservoir better. And again, the experiment that was done found that this, again, even with the boreholes as sources, the signal was way too weak. We were thinking about looking at the shallow reservoir, but we didn't get to that. So that's something, there is a resistivity model for the pilot model. So that's something that someone could do and should do, hopefully, but we didn't get to that. So right now, our results with EM are not positive in terms of getting a strong enough signal. There is hope that maybe for the shallow reservoir there is, and I was hoping that maybe we could see things as they come up the fault, as it gets along that fault in near to the shallow reservoir before it actually hits the shallow reservoir. But we didn't do a test on that. And Bill, feel free to correct me.
No, that's quite accurate, Mike. And it turns out that the model is there. The question is how to get the electromagnetic simulations done. Hopefully, someone will be able to access that model and do that. Yeah.
Yes.
Well, I think we're at the end of our webinar. Let's remember that this webinar is going to be on demand online for the next 3 months, I think. And so if you want to get your friends to have a look and see what's there, it shouldn't be a problem. And in addition to that, we want to appreciate the fact that it's been a lot of work on the part of the SEG to get the webinar in place. So thanks, SEG, and thanks to all of the presenters. I think it's been really insightful. We've talked a little bit about the reasons that we wanted to go forward with numerical modeling, the issues behind that, the complications, how it was done, how it could be used, how it is being used, and hopefully there'll be more examples of that in the future. So thanks for everybody. I guess we're all set to log off, Robin, and thank you.